Let's take a look at the Earth's atmosphere with an eye toward how it is warming from the sun's energy. The first thing we can think about is the fact that Earth has different surfaces, and in fact, not even different surfaces. The atmosphere has different characteristics that affect how much of the sun's rays are absorbed versus reflected. The quality of albedo is the reflectance of a surface. So you can see here in this image, this is a famous image called the Blue Marble, taken by astronauts on board the Apollo 17 mission to the moon. Really famous photograph of Earth. You can see here that the clouds clearly are quite white, meaning they're reflecting a lot of light, and so not a lot of sunlight is coming in if it's being reflected off. You can see the oceans are relatively deep blue, relatively dark, so they're absorbing more of that sunlight. You can see that some of the dry, sandy deserts of southern Africa as well as northern Africa here are uh, going to be reflecting a little bit more light compared to the forests of the Congo here or in say Mozambique area as well. The leafy green trees absorb more of that solar energy. So there's differences in the amount of sunlight that is received by any particular surface on Earth. But the other thing I want to point out about this photo is it really illustrates to us how thin the atmosphere is. The atmosphere is present in this photo, but it's clearly not that thick. And a lot of models that we see diagrams of the Earth's atmosphere overstate the thickness. Let's take a look at that right away here. Moving on to talk about different solar radiation, incoming solar radiation or insolation coming to the Earth. This is one of those diagrams where the thickness of the atmosphere is really radically exaggerated. Remember that the atmosphere is about 100 miles thick until you're in outer space. And so this is clearly not to scale because the Earth has a diameter of around 8,000 miles. And so the 100 over, 100 miles out of an 8,000 mile ball is a very thin layer, right? And that 100 miles is to outer space. In terms of breathable air, it's much, much thinner than that. So keep that in mind when we're looking at this diagram. What this diagram is showing, the distance that sunlight has to travel through the atmosphere at higher latitudes compared to at lower latitudes is really overstated. That's not as much of a factor in terms of reducing the amount of energy received at the high latitudes. The bigger deal is here in the tropics, the area between 23.5 degrees north and 23.5 degrees south, which is the area that the sun's direct rays fall throughout the year. In the summer, the sun's subsolar point moves to the north, all the way up to the Tropic of Cancer. In the northern winter, the sun's direct rays fall further and further south until all the way to the Tropic of Capricorn. But this area around the equator in the tropics receives direct rays of the sun, and that means that the solar energy is concentrated on the area. Whereas areas in high latitudes like the north and north and south poles are the most extreme, but even further north, higher latitudes towards the north or south poles, have a much more diffuse uh, area exposed. So that because of the angle of the sun's rays, the sun's rays hit at a more oblique angle, and so the amount of energy received by any given area is less because the sun's rays come in at an angle and they are less strong for that reason. This results in an energy imbalance. The tropics receive about 2.5 times more energy than the poles do. And then that drives global atmospheric circulation, which is our last diagram here. This is a nice little simplistic diagram. We're not going to get into the direction of wind yet. What I want to draw your attention here to is these circulation cells right here. And what we have is we have an abundance of heat at the equatorial region, and that results in low pressure at the surface and rising air. The rising air is because of the heating. So hot air rises at sounds familiar, I hope, to most people. So we have the conveyor belt here, if you will, of this air is driven upwards by the heating of the surface at and near the equator, and so all that rising air goes up, and it has to go somewhere, so it goes out, and we can see that happening here at the equator. It's going out at high elevations, and out here at high altitude is the correct term, and then for dynamic reasons, it descends here at about 30 degrees north and descends at about 30 degrees south. Hadley, who developed this model early on called the Hadley cell, had originally thought that it went all the way north and then came down and went all the way south. But what we actually observe is the Hadley cell actually is broken up at about 30 degrees um, north latitude and about 30 degrees south latitude. Now, because of that descending air is dry air. And what we can notice just from the way this diagram is done, this diagram is not perfect, but it's pretty good at predicting a lot of things. One thing that we notice is that the driest parts of the world are some of the driest deserts in the world, with high temperatures, not a lot of precipitation, clear skies for much of the year, are around this band around 30 degrees north. And then the same for 30 degrees south. There's not as much land mass down in 30 degrees south, but we see the Atacama Desert here in northern Chile is one of the driest places on Earth. We also see the Namib Desert here in western South Africa, also a very dry place. And not to mention Australia's Great Western Desert, for example, right? So the Hadley cell is a result of that heating, and these convection cells are a major way for warm temperatures, excess heat that's absorbed around the equator or in the tropics to be redistributed further north. And then this process is continued by these other convective cells north and south of the Hadley cells. They have less interesting names than Hadley. It's the mid-latitude cell and the polar cell, but they all serve this function of redistributing the energy where the equator is receiving, or the tropics are receiving 2.5 times the energy of the polar regions. So that energy imbalance is what's driving these convective currents, and as part of that process is redistributing the energy through the globe. Now, it doesn't quite even things out, but that's what's driving all of this convection. And that in turn is influencing our global atmospheric circulation, which we're going to cover later on.